Okay, so we're going to discuss the non-dispersive wave equation. And for some kind of wave variable, that could be something like the height of the sea surface, that could be the pressure in a sound wave, that could be the density in a sound wave. You get an equation that looks like this. So there's a speed here, there's our good old friend del squared, Laplacian, and then this side is the second derivative with respect to time. So by this point, you should be getting pretty relaxed with the idea of using separation of variables. So let's go ahead and do that and write phi as a function of t times a function of x and y. Plug that in, and we get t double prime, second derivative with respect to t, times x equals c squared times the Laplacian squared of phi, which we've now replaced with x times t. Okay, we can pull the t through because it doesn't depend on space, and we can divide at both sides by x times t, and we get t double prime over t. That t goes away. We get an x on this side. And so we're back to our normal separation of variables assumption, where now we have this side depends only on t, and so this side depends only on x. So if this actually depended on t, then you would never be able to match it by choosing an arbitrary x. And if this side depended only on x, you'd never be able to match it with a set of t. So we know that both of these are going to be constants. And let's choose our constant carefully here, because we are going to try and make ourselves, save ourselves a little work. So t double prime over t, let's call it sigma minus sigma squared. So the expectation here is that this is going to be an exponential, and we're going to want it to have a complex exponential form in time, because we think that waves go up and down, right? So that's how we chose the minus sign. Okay, great. So we can solve this part of the equation, minus sigma squared t prime over t double prime, and we choose it, we do it with our normal guess and check. So t is equal to some initial coefficient times a e to the minus sigma squared I sigma t, and we can make this one the plus one, call it a plus a minus e to the minus I sigma t. Cool. All right. What about the other side? Look at this. This is going to be just a Helmholtz equation. So we have c squared del squared x equals minus sigma squared, and we can bring it to the other side, plus sigma squared x equals 0. That's our good old Helmholtz equation. We can move the c squared if you like to make it even more clear. Okay, so the Helmholtz equation, we know how to solve that. We do a guess and check again because this is a homogeneous equation. So let's assume that x equals e to the ikx, and so we don't really know the relationship between k and l yet. Between k for the x part and l. So let's stick this together. Let's make this a plus root, and we'll have a minus root, b minus e to the minus ikx. And now let's stick on, put a parenthesis over here, let's stick on a dependence on y, and that would be an exponential. I'm going to jump ahead a little bit and make it, and we're thinking of a two-dimensional wave equation here. I'm going to jump ahead a little bit, and I'm going to make this one, I'm just going to call it c plus e to the I lx, and plus c minus e to the minus I ly, oops, y. Okay, so there's a guess and check style solution. It's got 3 coefficients, and they're going to be somewhat redundant, but we're going to match it again in the end, and we'll come back to that when we get to the initial conditions. And notice that I've chosen in every single case a complex exponential. That's because I knew it was the wave equation to begin with. If I didn't choose a complex exponential, if I had chosen a minus instead of a minus sigma squared, a positive sigma squared, I would have regained that when I go through and figure out the constraint on all of the sigmas and c squared. So let's figure out what that is right now. Okay, if we take this x and plug it in here, we're going to find the spatial constraint So taking the first derivative of this, second derivative of this, it just brings down a k in both terms each time, and actually an ik, so it becomes minus k squared. And then if we do the second derivative with respect to y, it brings down a minus L squared times x. That's equal to the Laplacian of x. It's equal to that. And what is that supposed? That's just plugging into here. And then that's supposed to be equal to minus sigma squared over c squared times x. And so if the x is not equal to 0, if this is a non-trivial solution, this is actually a homogeneous equation because both sides depend on phi. If phi was equal to 0, we would have no waves, but we would also have just a trivial solution. We're looking for a non-trivial solution, so we don't think that x is equal to 0 at least everywhere. So we can divide through by x, which gives us the relationship k minus k squared plus L squared equals minus sigma squared, or more simply, c squared times k squared plus L squared equals sigma squared. Or if we wanted to solve it for sigma, we can take the square root and put it that way, and there'd be a plus or minus there. This is a special kind of equation in a wave equation. This is called the dispersion relation. The dispersion relation for a plane wave, and our guess and check solution here is what's called a plane wave solution, because all of the x direction, all of the y direction are setting out these crests and troughs that we're thinking about as wave crests and troughs that'll be propagating. If you think for a second what this would look like, it would have crests and troughs in it, and then it would also be propagating. And there's a relationship between the specific crests and troughs, the k squareds and L squared, so the wave number, this is called, which is 2 pi over the wavelength, times c squared. This is the speed of propagation. This is 1 over length. This is a velocity, so it's a length over time. So this whole thing becomes a frequency squared. Take the square root, and now we have a frequency over here. So we have a relationship between the frequency of the wave, the speed of the wave, and the k squared and L squareds. Okay. So when waves satisfy this dispersion relation, which we can simplify a little bit more, if we take this square root, we can make it plus or minus c times, this is the length, the magnitude of k squared plus L squared, which we could just call the magnitude of kappa. That, where kappa squared is equal to k squared plus L squared. And the reason why we do this part is because this is now the wave number regardless of the orientation of the waves, and this is the wave number in x, this is the wave number in y, and look, it looks like we have a nice Pythagorean theorem thing going. So this is, we can think of k and L as parts of a vector. This is the length of that vector, kappa, and so kappa is the wave number for the whole wave. So this is a special kind of relationship which says that the kappa, the length of the wave number, is proportional to the frequency. And when that's true, it actually means that all the different waves propagate at the same speed. The crests propagate at the same speed, the troughs propagate at the same speed, and waves of any wavelength, their wavelength changes, but along with it, so too does the frequency. So the frequency, if we look back up here, is sitting still, not letting x and t change. It's just going up and down in time. And if we're sitting in a particular place x, we're seeing it up and down and up and down in x. We're seeing it up and down and up and down in y. We put it together, and there's a relationship between the up and downs in x and y, such that as the wave propagates by you, you're going up and down, just as the crests and troughs are propagating by you. That's what happens in this dispersion relation with this particular proportionality between the wave number and the frequency. That kind of wave where it does that is a non-dispersive wave, because all the waves of all wavelengths travel with the same speed and velocity c. So, c is directionless in this point, but the speed c and then in a direction that has to do with the orientation of this k squared and l squared. We still haven't figured out what the direction is yet because we haven't plugged in any initial conditions. Let me undo a bit of this. We'll clean things up. Okay, so we've tidied things up by just collecting together the t solution and the x solution, the x dependence of the x solution and the y dependence of the x solution, brought it back together into one combination. And the combination that I have is kx plus ly plus sigma t and kx plus ly minus sigma t. And so let's think about what these mean. If x is increasing, or kx plus ly is increasing, that is if we're moving in a particular direction along the waves, then t could be increasing at the same time in the right relationship so as to make this coefficient stay fixed. That is, there is a direction in space and time where the phase of the wave is unchanging. That's the propagation of a crest or a trough. That x, y, and t works like that. And let me draw you a quick figure. So if we think about k as being a wave number in the x direction, L being the wave number in the y direction, then this kappa, the thing that's the sum of the squares, the magnitude, we could really think of it as a vector. And so the direction of this vector dotted into the position, wherever you are, that's exactly what this is increasing. If that's increasing, so you're getting farther and farther out along this direction, then time has to be increasing to keep the phase fixed. So you can imagine these wave crests all moving. The phase, when this reaches a maximum, is when you have that positive phase like that. There are a few other things I want to touch on. What about this one? Well, this one does the same relationship, except it's KL plus sigma t. So it's a wave propagating in the opposite direction along K and L. But remember, all solutions of this form are going to be fine because they are all built from our guess and check solution. And since this is a linear equation, we can add these on top of each other. So really, properly, we should be summing up over all K's and L's, which gives us both a positive and a negative direction. And the sigma here is not any old sigma, but it's the sigma that matches with the dispersion relation sigma. So you give me a k, I calculate a kappa, and I can tell you what sigma is for a given c. That's the relationship. So the sigma is not a free parameter. It's locked by the dispersion relation to the k and l you choose. And then there's one more thing. Since these are complex exponentials, this whole beast over here is complex. At least I had it in my mind that phi was a real number, that it was a measurable thing. This would have both complex and real parts. But actually, the real part, the observable part, is just the real part of this whole set of equations. Okay, so what's the real part of this? Well, if A was real, then it would just be cosine of kx plus ly minus sigma t. If A was pure imaginary, it would be sine of kx plus ly plus sigma t. So depending on what complex number we choose for this, we could have a whole combination of sines and cosines. Hey, this is just our Fourier transform that we already talked about. This is the complex Fourier transform. We're particularly interested in the real part, which is representing waves. And instead of a Fourier transform in x and a Fourier transform in y, like we talked about before, this is a Fourier transform in x, y, and time, except the time part is locked through this dispersion relation. So there's a particular frequency for a particular wavelength as these waves are propagating around, and you can superimpose waves going in all different directions with all different wavelengths, and you can still explain it with this formula right here. And all of them are satisfying that wave equation. How do we find the A sigma and the A sigma minus? Well, we just need an initial condition or a boundary condition. We didn't talk about the boundary conditions for waves. These are all periodic functions, so we could think of the waves as being periodic in a large domain. Or in fact, we could put a solid boundary somewhere and have the waves bounce off of the wall. That's a slightly different condition, but it's something that we still know how to manage from just thinking about these sine and cosine series as they approach the wall, and having no normal flow through the wall is a condition on the sines and cosines that we could work out. That's the intro to the wave equation. Thanks.